All right, everyone, let's go to slideshow. All right, y'all, it is June 29th, 2022. Let's get started. So we're going to go over some highlights from the progress report from the iteration 6. We're going to go over the factory pattern for all drivers and what that kind of means, the implications of that. Changes to the pole handler, because I explained it a lot last iteration. I had some difference in opinion afterwards, so we're going to go into that a little bit. And then also going to go over percent scale and how it's actually, and what it can be used for. All right, so progress report. We got scale in, percent scale. This is actually a predecessor to getting in the linear potentiometer. I'll be going over that in a little bit. I went over the idea, so I added this last minute to this sprint because it was actually something that I realized we need to consider, which is what happens with constructors if they have to fail or they have an error occur in them. And this is actually what led to that poll regarding what the name of the factory function should be. I'll go into that a little later. Timeout timer. This is finally putting in the timeout timer type stuff, but mostly just putting in embed timeout. I'll go over that. We got the mock input pin, the SPI output pin, which is great. The potentiometer's in, and we also got rotary encoder in, so we got a new interface in. So I'm pretty happy about that. Okay. Yeah, so let's just get right into it. So factory pattern for all drivers. So first I'm going to explain what a factory pattern is. It's formally a factory is a function or method that returns an object or a varying prototype or class. That's just simply to say that we can use it to have a function that we can then give it some parameters. It'll do some work, and then it'll construct an object for us. Now, why would we ever need a factory to build to build this thing out? There are a lot of reasons to have factories in a variety of object-oriented programming models, but for the most part, for us, it comes down to one basic fact. Constructors only return themselves as an object. So if you have a LPC output pin, it can only return itself. Therefore, you could not get information about an error out of it. Now, there is technically a technique that Leaf has that makes it such that you can get that error information out, but it's only used as a last resort, usually when when trying to use Leaf with a C-style callback, where the C-style callback might be like a status code, or that callback could just be void, but you have to put some things in there that could actually error out. So in those cases, you can actually run the new error function from Leaf and create that, and basically create that new error. And then on the outside, you have to do an extra check. You have to do a manual check. There's no way to get around it. But having to do that for every single constructor is actually not a good idea. Especially because it's so easy to forget. That's the whole point of why Leaf is really useful, is because when you have that return type of result, it'll always yell at you saying, hey, you've got to actually touch this result. At the very least, you get a warning telling you that something's wrong. So that's not going to work. Another idea that I had was prefer maybe exiting. Well, that's cool. If we do exit, that's useful, because maybe during that, maybe we can come up with a situation in which exit makes sense. Because there's this thing called @exit. It's a C function that basically creates a callback, stores a callback in a list of global function pointers. And when exit is called, it will start running through all those function pointers, all of those different handlers. And when it finishes up those handlers, it'll do its last little bit of work in order to clean up the system. So @exit has really seemed pretty useful. A couple of issues with @exit is that those calls happen regardless of if you exit abnormally or if you exit normally. Another thing is that we now have this global set of queued up handlers, which may not respect your operating system that you're using. So that's another thing. On top of this too, 32 pointers, that's kind of significant. And the worst part of all of this, that actually was pretty much the killer of this, is that you are forced to dynamic allocate, just period. So because of that, basically if you ever exceeded the 32 handlers, it will start dynamic allocating. So that's the reason why we didn't really go with it. So I was looking for other alternatives, talked to the maintainer of Boost Leaf, and they pretty much told me, yeah, make a factory. make your constructor private, make a factory. The factory can return back a result or your own object. So that is the solution. Now I'm going to show you how it's supposed to look. So here are a couple of code snippets. We have a class peripheral and a driver on the other side. There is a distinction between the two, and I spent some time considering, should they just be exactly the same and how they should be formatted. So one of the patterns for libembededhal is that ownership of peripherals should be squarely at the driver level, meaning that you get the privilege of borrowing and using the object and calling on it, but you don't actually own it. In other words, you make the variable static to the function so that it pretty much is owned by the function. So within that namespace, it's not accessible outside of that function. Now the idea here is that by doing this, every time you call this function, you're basically grabbing the same reference that you grabbed last time. So if you have an I2C1 and you grab that reference, you try to do a get on it, you're not creating a new I2C object, you're getting back a you're getting back a reference to that object that was constructed at the time when you first called it. I'll go into more details about that in a sec. So that's one idea when it comes to peripheral drivers, and that's because there's a finite number of devices, and it does not make sense for you to be able to make 5 I2Cs that have different state among themselves that may have a different tracker for like what buffer they're using for the peripheral. There's only one I2C. There's only like n number of I2Cs. There should only be n number of their drivers available. There is a way to create and construct. I'll still make available and have as a protocol that you should be able to construct objects outside of the factory getter, just because it's important to not have singleton be the only way to construct these objects, but that'll also be its own factory. And in that case, it's not as safe to use that particular driver. You have to be very careful not to mix that up. And just to make sure it's very clear, if you're concerned about thread safety and that kind of thing, we are working on actually adding in thread safe wrappers for each one of the peripherals, such that you get that reference passed into that wrapper, and then you have the wrapper distribute out implementations of the thread safe version of that peripheral so that other things can use it. So you should never actually use the get function in a way that is used across different threads. That's a race condition. And you need to make sure you use some sort of wrapper or have some code that manages who gets access to these peripherals, which is how you do it anyway with C or any other language. So that's the peripheral side. The main thing to here is to get that we make a static peripheral object and we return a reference to that. On the right-hand side, we have a create function. That's the name I decided to go with. That's what most people pretty much said yes to. I was looking at make and construct as well. Make felt a little bit weird, honestly. Not sure why. And then construct actually felt really good. So honestly, I may just switch over. If anyone has a big, if anyone feels really strongly about construct and has some reasons why it should be the way we go forward, I'm more than fine with using construct as well. But create and construct are pretty close. But yeah. So here, when it comes to create, you're actually creating a new object because there's no limit to the number of objects or devices that you can have in a system. There may actually be, but we never really know, So for example, MPU 6050s, we could have, in a deterministic, but n number of them. And you can do n plus 1 if you wanted to. There are all these clever ways you can basically have a system where you can have n number of MPUs or n plus 1 MPUs. I2C buses, all that kind of, I2C muxes is what I meant to say. Being able to, do address translators, that kind of stuff. So with all of that, you can basically really map out and have a whole n number of these things. So there's no reason for the actual class to have ownership of this object. So you're going to actually have it be moved out to the caller. So that's pretty much the only big thing here. Is the fact that you're able to actually create individual objects for the devices, for peripherals. The peripherals themselves own it. In the case of the device, the caller is the one who owns it. The next slide just goes over these details. So one of the things that you may have noticed in that bit of code before is that both of them had their copy constructors deleted. This may change if I see any reason why this should not happen, but for the most part, the idea of having a copy of an object that's supposed to reference the same thing seems like a bad choice in development. I think that I think it's a bad design. So So yeah, so copy constructors are pretty much eliminated. So you should not be able to make copies of the same driver. Now you can move them. All drivers here need to be movable. Two reasons actually. One is that Boost Leaf actually requires that the object you put into it is movable. If it's not movable, then it won't work. So move constructors have to be there, but copy constructors should not be. Now, onto the next area, rules for peripherals. So their factory name must be get, because you're actually getting an object. You're not really creating a new one. That's why I decided not to use create there. The peripheral drivers are lazy initialization. So they will initialize once for like their object, and after that, they will just simply return back a reference to that object. Factory functions, a factory function must statically allocate the peripheral and hold ownership of it. So just make sure you put the static keyword in there. And then finally, factory returns a reference, just like I said, multi-sin pattern. Now the rules for the device drivers that they should be named create, and that we need to basically move ownership of that object out to the caller. It should not be held within the driver itself. Any questions on the factory pattern? Cool, awesome. Note that like this doesn't have like if you're working in libembededhal, this actually doesn't affect you. This is mostly for implementation. So if you're working on liblpc or libstm or any of the other libraries, this is you'd have to worry about this. But otherwise, most of the code in libembededhal does not have to worry about this. Okay. So next up, changes to poll handler to this embed timeout. So simplify the definition of timeout in libembededhal. Before I had this long conversation about like all the different ways you can basically use timeout. Now, most of them made sense, especially the time-based ones. But the signal-based ones kind of put a weird taste in my mouth after I had done the video, because I thought about them a little more, went on some walks, and decided there's some issues, some categorically bad issues with having timeout associated with when a particular like UART gets all of its bytes in. So I decided to kind of just go straight full time-based. And also with that, I decided to also kind of trim some other things out as well. So if you look at the signature here, it now takes no arguments and returns nothing. Well, it can return a boost leaf result. And in this case, the idea is that you either get back success from the timeout function, or it returns back an error. And that error has to be timeout, but it can actually be more than just timeout. It can be whatever things results in that error occurring. Like for example, a counter being misconfigured or having some invalid settings or something like that, just to get all the information back. But timeout has to be one of those errors that is returned in order to be conformant. The new definition is that a timeout is a definition really, but is a definition of a callable object or function that signals to a procedure that the procedure has exceeded its time allotment and should return control to the calling function. It should throw embed error timeout if a timeout occurs. That is the idea of timeout, and that's pretty much the end of it for the most part. The concept of signal-based timeouts have been removed. This also had some really cool fundamental changes to delay and possibly even other functions in the future. And I want to show you what that looks like from this PR here. So from here, so the name's actually been changed from like, ag timeout timer, but to create timeout. So there's some other changes here to fix some things up. But we have this counter timeout functor. I believe it's a functor. Yes, it's a functor. A functor is a function object. So basically any class or structure or any object that basically implements the operator parentheses is considered a functor. It looks a little weird here, but it's like you can think of a little space being there. So the idea here is that this functor is actually like a helper function for basically creating, or it's supposed to be the timeout object. So I'm going to go down a little bit further and show you the create timeout function, which I'm going to then look at this thing, view this file directly. Here we have a create timeout function. You pass in a reference to a timeout. You pass in the amount of time you want this timeout to go for. Do a little basic checks. You do a few calculations. And then when it's all done, you can then return back this counter timeout, or if some error occurred in doing any of these operations, return that error. And then here we have something interesting. We have counter, the duration, another balance check. Most importantly, oh my goodness, I just realized I can remove this check because this check's already handled here. I'm going to remove that actually in a little bit. Didn't even notice that. But yeah, here we create the timeout, put in boost check here, create the timeout, and then we run delay. There's now a universal delay function that works with basically any timeout object. So if we go back here, or yeah, go a little further here, you can see the implementation for the delay function. If I can find it. Yeah, add timeout should be in here, unless it is in a previous change. It might be in a previous change. Okay, well, I can just show you guys directly. So go here, libembededhal, and it is in the timeout header file. And it's this function right here. So inline delay, you pass in a timeout object. It is templated so that you are allowed to, if you pass it in normally, then it should actually use this std function. But you can also, give it a force type so that this thing can all be inlined or, template instantiated so that's faster for performance reasons. Yeah. So here you pass in a timeout object, a little bool saying whether or not it's waiting. And now you're just going to basically continually run try handle sum, basically continuously run the handler to see if it returns back success or failure. If you get any failures that are of timeout and just timeout, then you change waiting to false, return to success, get out of this thing, return here. If there's any other errors, then this last check will actually make sure to return them back from where they came. So yeah, so that is the new timeout stuff. Oops, daisy. That should actually simplify things a lot. I think that we can actually, if we have concepts, this isn't a concept, but this is a type, but like if we had concepts like this that can be easily placed around in different areas of the code, that'd be really helpful. That'd be really nice. Yeah, and I think the last thing I'll add here is that I had a little bit more thought. I may have talked about this last time, but I am planning on adding and making I2C's transaction method incorporate a timeout object using std function, just because you have to make sure it's polymorphic. But I'm going to place a timeout function there so that whenever a peripheral device external to the MCU is clock stretching, we can time out for that. Otherwise, clock stretching, a timeout for the transaction is actually not necessary. So yeah, so that's embed timeout. Any questions on that? Okay. And then finally, we have %scale. So %scale allows a user to safely, is a safe method for basically scaling up and down values. I'm going to show you what it does. Lee is the one who worked on this one. And check this out. So the idea here, I'm actually going to look at one that might make a little more sense, and I'll show you the one above. So here, let's say that we have some percentage value. Let's say it's 50. And you have some number between, like you have some range of some, and it goes from 0 to 200. If you take that percentage value and you give it those two bounds, you should get back out 100, half of the middle point. The rationale for doing this is that me and Malia actually kind of discovered something when it came to developing the linear potentiometer class. So ADC returns back a percentage relative to the full scale amount of the ADC's voltage range. And if we wanted to have bounds for let's say we have this linear potentiometer, we only want to read between not like the full range, or let's say the potentiometer's voltage doesn't go from the full swing from 3.3 volts to 0 volts for some chip. It only goes from 1 volt to 2 volts, okay? So that means the percentage value is going to be some portion in the middle, 33% to 66%. If you read a value, and actually before I go there, let's say we have 0 to 90 for a range for the potentiometer, and then we also have 30% to 66%. I'm sorry, 30% to 60%. Okay. How do you go about scaling whatever value you got from your ADC into that final length value or that final angle value? Well, in this case, what you do is on two parts. Number one, you scale it against the percentages. So this actually stretches out whatever percentage you have from into 0 to 100%. So you can think of 30% and 60% as being your 0% range and your 100% range. Basically map anywhere between those ranges into the new 0 to 100% range. This is important because after that, you can then take that range from 0 to 100%, and then throw a value 1 and a value 2 to it, a range, and then that will then make sure that whatever value you have, it gets you right where you need to be. So again, if the percentage, if you had a range between 0 and 90 degrees, and the ADC value that you read was somewhere smack in the middle, gave you 50%, you would stretch out this 30 and 60% out to 100%, and then you take that new value, then multiply it against your range, and that will pretty much give you exactly what you're looking for. And yeah, that's pretty much what percent scale does. And it should actually, whereas in Arduino and other places you'd have a map function that maps two inputs and an input, a range, and then the output range. This is the same thing except using the percent class, built into the percent class. That one's a bit of a doozy. Any questions on that? Cool. Alrighty. And that is the end of this presentation.